Welcome to this video, where we will review the difference between push and pull systems, as well as just-in-time, one-piece flow, FIFO lane and the concept of supermarket. First, let's see the push and pull system. In a push system, a traditional factory pushes manufacturing orders for its products through the productive system. Typically, in push systems, the inventory at the entrance of a process is not limited, it is independent of the inventory of the rest of the processes. That is, push systems allow inventory to float. Conversely, in a pull system, components used in the manufacturing process are only replaced once they have been consumed, so companies only make enough products to meet customer demand. Therefore, in a pull system, the introduction of work into the value stream is a function of the system's inventory, which is usually limited. In other words, in a push system, execution is performed in anticipation of an order, demand is forecasted, and it has a proactive process based on projected need or demand. Meanwhile, in a pull system, execution is performed in response to an order, demand is actual and known with certainty, and it has a reactive process based on actual need or demand. Now, you can see examples of both systems. On the left, the push system means to produce items ahead of the demand. Thus, products are made to create inventory based on demand forecasts. Products like those in a supermarket are examples of a push system. On the right, the pull system means to produce items only when there is a customer demand for them. Thus, products are developed based on actual demand, rather than forecasts. A sandwich or a hamburger in a fast food restaurant is an example of a pull system. As an analogy, the chain represents both systems. On the left, if we push one end of the chain, it will deform. On the contrary, if we pull one end of the chain, then it will be extended, maximizing the flow. You can learn almost everything about logistics from a sandwich shop. For example, if sandwiches are made considering up to 18 different bread types, 6 different proteins, 10 spreads, and up to 20 different toppings, then, potentially 21,600 unique sandwiches might be made. However, none will be made ahead of time. Instead, sandwiches are made to order. But other products like juice or yogurts are already made to stock, while other special products are made just when requested, i.e., engineered to order. Similarly, 3 sandwiches with different stories. The first one, the turkey wrap, is a product with high demand, so the raw materials are bought, components are prepared, and the final assembly is made ahead of time. Thus, when the customer buys it, they are pulling the process. The second one, the signature ham sandwich, is made to order, that is, the materials and components are ready, but the final assembly occurs just when the order has arrived. The third one is designed by request, and then the rest of the steps are followed. Using just a push process leads to higher inventory, while pull processes are rare. Instead, mixed systems are common, combining steps of both systems, usually pushing at the beginning of the process while pulling at the end of the process. Now let's go deep into just-in-time. Just-in-time, JIT, is an inventory management method whereby materials, goods, and labor are scheduled to arrive or be replenished exactly when needed in the production process. The ideal state is that a workstation receives materials from an upstream process exactly when those materials are needed and in the quantity required. In fact, just-in-time is considered one of the pillars of the Toyota production system. While just-in-time is often utilized in production cycles of low complexity, just-in-sequence, which is a more advanced approach, excels in complex production environments because various parts are delivered in the order of assembly. Just-in-sequence allows for much more flexibility than just-in-time and traditional manufacturing methods. Original equipment manufacturer, OEM, is the final stage from a supply chain perspective, where the final product is made. Due to just-in-time, JIT is a production and inventory strategy aimed at reducing waste, lowering inventory costs, and ensuring materials or components arrive exactly when needed in the production process. OEM relies on suppliers located in levels Tier 0.5 supplies preassembled modules, usually inside of the OEM facilities. Tier 1 are those suppliers responsible for supplying major systems or modules. Tier 2 suppliers are those of Tier 1, while Tier 3 suppliers are those of Tier 2, and so on. Does just-in-time work with any type of process? Just-in-time works best for companies using repetitive manufacturing functions. Hospitals, small companies, and other entities may not find JIT feasible. JIT requires a very stable production system, characterized by continuous flow, reducing MORA, and without excessive burden, MURI. JIT then not only is possible but, by definition, reduces waste, MUDA, from the product process matrix. The just-in-time approach is feasible in processes with connected line flow, that is, assembly lines and continuous flow. Those kinds of processes, such as an automobile assembly, are characterized by moderate to limited product variety, but highly standardized products. One-piece flow means that parts are moved through operations from step to step with no work in process, WIP, in between, either one piece at a time or a small batch at a time. This system works best with a cellular layout in which all necessary equipment is located within a cell in the sequence in which it is used. Therefore, achieving one-piece flow helps manufacturers achieve true just-in-time manufacturing. In a typical batch and queue manufacturing environment, parts move from functional area to functional area in batches, and each processing step is controlled independently by a schedule. However, there is little relationship between each manufacturing step and the steps immediately upstream or downstream. This kind of process arrangement conveys several deficiencies, such as large amounts of scrap are created when defects are found in large batches of VIP, long manufacturing lead time, poor on-time delivery and/or lots of finished goods inventory to compensate. Large amounts of VIP. In a connected flow, there is a relationship between processing steps. That relationship is either a pull system, such as a supermarket or FIFO lane, or a direct link, one-piece flow. One-piece flow is the ideal method for creating connected flow because the product is moved from step to step with essentially no waiting, zero VIP. However, one-piece flow is not always possible. Why would we not always create one-piece flow for every set of processes within a value stream? To be good candidates for one-piece flow, we must have the following conditions. Processes must be able to produce good products consistently. If there are many quality issues, one-piece flow is impossible. Process times must be repeatable as well. If there is much variation, one-piece flow is impossible. Equipment must have very high, near 100%, uptime. Equipment must always be available to run. Processes must be scalable to talk time, or the rate of customer demand, flexible. When implementing just-in-time, a pull system is essential. The JIT connects through pull systems those processes that have not been possible to create a continuous stream, for example, monuments, heavy and bulky equipment whose location change is not feasible, unreliable equipment with significant chronic losses, machines with long changeover times, expensive machines shared with other product families, whose duplication is not feasible. Processes must be scalable to talk time, or the rate of customer demand, flexible. In the pull systems proposed by the JIT, the upstream process will not produce without the authorization of the downstream process. Here, the FIFO lane and supermarket are used for this purpose. Examples of pull systems that mainly reduce inventory and consequently lead time are FIFO lane, supermarket, Kanban, Conwip. Let's see FIFO lane. A FIFO lane connects two processes to ensure materials or products are used in the order they arrive, avoiding overstocking, product obsolescence, or quality issues. The FIFO lane might be a conveyor, a rack, a trolley, or any physical connection between the two processes. The operating rules of a FIFO lane are the following. The customer process must maintain the sequence of product input, first in first out. In the FIFO lane, WIP inventory, that is, work in process inventory, is physically limited to a certain number of pieces or boxes. If the FIFO lane is full, i.e., the preset VIP has been reached, the supplying process must stop production until the customer process consumes products again. Let's review the following example. The supplier process, P, must provide items to the customer process, cell C. The current talk time is 2 minutes. Our first approach to solving the number of items that must be supplied for the FIFO lane is by considering the MTTR, that is, the mean time to repair. Machine P suffers from chronic breakdowns that cannot be predicted, and its repair time is considerable. Due to these reasons, in the current situation, it is not feasible to create a continuous flow and integrate Machine P into cell C. The next option to connect both processes is through a FIFO lane. The talk time of the customer, cell C, is 2 minutes. The MTTR, that is, mean time to repair for Machine P, is 480 minutes. And the company has established a safety factor of 25%, which is an extra 25% of items for security reasons. We compute the maximum work in process, WIP, by dividing the MTTR by the talk time and then multiplying by the safety factor. For this example, the maximum WIP for the FIFO lane is 300 items. Now, for case B, we will use the changeover time to estimate the maximum WIP. Machine P is bulky and has a high changeover time. In addition, the cycle time is short compared to the talk time of cell C. For these reasons, it is not feasible to integrate it into cell C. The next option to connect both processes is through a FIFO lane. The talk time of customer cell C is 2 minutes. The changeover time for Machine P is equal to 300 minutes. The safety factor is 20%. Now, we consider connecting via a FIFO lane, a shared resource, either before or after a process. Case C implies a shared resource. Paint spends a particular time repeating a specific sequence, for example, FIFO 1, FIFO 2, and FIFO 3, to process the products from the different FIFO lanes. In this case, FIFO 2 from assembly must be sized to accommodate the inventory generated during the period of the aforementioned sequence. Talk time of the flow stream is equal to 2 minutes. Time for the sequence FIFO 1, 2, 3 is 240 minutes. Safety factor is 25%. We substitute the values in the equation, thus, the time for the sequence is divided by the talk time, then multiplied by the safety factor. For this example, the maximum WIP is equal to 150 items. Let's see now the supermarket as a way to pull a process. In lean manufacturing, a supermarket is a controlled inventory storage area where a predefined amount of parts, materials, or sub-assemblies is kept to supply downstream processes. How a supermarket works. All products consumed by the customer must always be in stock. Products are presented in standard boxes or specific devices, depending on the physical characteristics of the product. Several customer processes downstream can consume products from the same supermarket. The inventory of each product is limited. The supermarket belongs to the supplier process and can be located next to it or next to the customer process. The customer process removes the products it needs from the supermarket just when it needs them. The removal of a box from the supermarket generates a Kanban signal that authorizes the supplier process to replenish the consumed product. In lean manufacturing, the supermarket and Kanban are usually joined together. The supermarket provides the controlled inventory buffer, while Kanban provides the signal system to replenish it. Together, they create a pull production system. How supermarket and Kanban work together. Customer process, downstream, takes parts from the supermarket whenever needed. When stock is removed, a Kanban signal, card, electronic tag, bin, or visual marker, is triggered. This Kanban travels to the supplier process, upstream, telling it exactly what, when, and how much to produce. The supplier replenishes the supermarket with the same quantity that was withdrawn. The cycle repeats, preventing shortages but avoiding overproduction. In the following presentations, we will delve into Kanban and other concepts,